Alright, so mass number is the sum of protons and neutrons. An isotope is different forms of the same element that differ by the mass number. So, for example, we have hydrogen. So this form of hydrogen has one proton and no neutrons. This form of hydrogen has one proton and one neutron. And this form of hydrogen has two neutrons and one proton. Synthesis is the kind of reaction where two elements, typically two, it could be more, but two elements, or it could be two compounds, come together and form a new compound. So we can sort of represent it like that. Metalloids, so we have metals and we have nonmetals. And then we have a few elements that are kind of on the line. So for example, metals conduct electricity. Nonmetals don't conduct electricity, so we have a few things like silicon or arsenic that conduct a little bit. So those are metalloids. And Dalton was the first person to come up with what we call the modern atomic theory. So developed the modern atomic theory. So you should know the different things that Dalton said. Modern atomic theory. So, among other things, Dalton said that all matter was composed of atoms, that the atoms were indestructible units. All atoms of a particular element were the same, so all hydrogen was like all other hydrogen. And probably most importantly, that in a chemical reaction, you just had the rearrangement of atoms, that atoms weren't created or destroyed. The cathode ray tube experiment was the experiment that established the existence of subatomic, or of the first subatomic particle, which was the electron. Essentially, you had the metal here, and it was there was a voltage applied across these two metal plates. The electrons were accelerated. They probably weren't called electrons then, but the particles were accelerated. And I guess most importantly, what was found was that you could bend this ray. So if you put a positive charge and a negative charge, what would happen is you could bend this ray. So the other thing is that no matter what sort of metal you put down here as the cathode, you still got the same, particles with the same properties. So again, the significance here was that it was the first subatomic particle. So you should be able to answer questions based upon the representation. This is sort of the nuclear form representation. So if you look on the periodic table, you'll see that potassium has 19 protons. And since there's a plus charge, that means that one of the electrons has been lost. So typically, potassium would have 19 electrons, but in this case, it would only have 18. The mass number is 39. So I'll do one more. You should be able to do all of these. So you would look on the periodic table and see that the element with 16 protons is sulfur. And since the mass number is 32, you know that the number of neutrons is 16, and you have that there are 18 electrons, so that means that there's a 2 minus charge. So you, I think, without any problem, can probably do the rest of those. So this is sort of a variation of what I used to explain the mole concept to you at the beginning. So if you look, you've got one atom of oxygen, one atom of sulfur, so that means the ratio of atoms is 1 to 1. But the mass ratio is going to be 1 to 2 because the mass of a sulfur atom is twice as much. And then you can just continue on. So if you had 10 atoms of oxygen, that would be 160 AMU, and this would be 320 AMU. And still the ratio of the atoms would be 1 to 1, and still the ratio of the masses would be 1 to 2. So if we continue on, eventually we could get to a point where we had added 16 grams of oxygen. And if we were always adding an oxygen every time we added a sulfur, then we would also have 32 grams of sulfur. In that case, the ratio would still be 1 to 1, and would still be 1 to 2. And that amount, the way that we get that amount is just by taking the AMU number in grams, and we call that amount a mole. So a mole, the way you obtain a mole of oxygen is you take 16 grams. The other thing is, of course, when you have taken a mole, you will have 6.02 times 10 to the 23rd, of whatever it is, but in this case, atoms. Okay. Okay, so I went over most of this in class already, but let me just say a few things about it. First of all, you need, of course, to know how to get the molar mass. So you do that by taking, in this case, it's 1 carbon, so that would be here 4 hydrogens, and then 1 oxygen. When you add those up, you get 32 grams per mole. So the 32 grams per mole becomes our conversion factor. So over here, what I did is I took 13.4, which was the amount given, then multiplied it by the conversion factor of 1 mole over 32 grams. And when I do that, I get 0.419 moles. Then I'm going to skip down, just because logically I think it makes more sense. So down here, I take the 0.419 moles, and I multiply it by this conversion factor. So we know that one definition of a mole is that it's 6.02 times 10 to the 23rd of whatever we're talking about. In this case, we're talking about molecules. So when we multiply, then over here, we get 2.52 times 10 to the 23rd molecules. And you could use this same sort of notation that you use with else. That's okay. Now at this point, we can go up here, and we take our number of molecules that we just found. And if we look at the formula, the molecular formula for CH3OH, we see that for every molecule, we have 4 atoms of hydrogen. So this is our conversion factor. And when we multiply, we get 1.01 times 10 to the 24th. All right. For total atoms, the only thing that's different from B is you're just multiplying times the factor of 6 atoms per molecule. So that's 1 carbon, 4 hydrogens, and 1 oxygen for a total of 6. And then in the last part, something that we'll use a lot more later, if you have 13.4 grams of CH3OH, then you know that for every 32 grams here of CH3OH, you have 4 grams of hydrogen. So this is, again, just a conversion factor, and that gives us 1.68 grams of hydrogen. All right, so on the periodic table, we have the alkali metals, which are these, but remember, excluding hydrogen, because hydrogen is not a metal. So that's the alkali metals. Then in the next column here, that's the alkaline earth metals. The transition metals or transition elements are from here to here, so this sort of section in this part of the table. Then we skip over a little bit. We have the halogens in this column and the noble or inert gases in this column. We also have a line here which goes like so, and to the left of that line is the location of the metals. So there are a lot more metals than nonmetals, which are to the right of the line. And then we have the elements that are some of the elements that are on this kind of staircase, and those are the these are the metalloids. For condensed formulas, what we do is we just take, so I'll do this one up here first, we take the hydrogens and we just sort of clump them around the atom that they're connected to. So that's the CH3 part. And then the reactive part, which is referred to as the functional group, we put by itself. So on the next one, methyl chloride, we'd have CH3Cl. We also have the molecular formula. So on this first one, the molecular formula is, I'll just do it like this. So the molecular formula is just a listing of all of the different types of atoms. So on this one we had C2 and we had H4 and we had O2. And this one is already in the molecular formula form. These questions are taken from the lab, and we went over these in class, so you should be able to look at your lab and see the answers to these. But the first one is a decomposition reaction. So decomposition. And remember that the way that before we do the testing, the way that we made the reaction go faster is we added a catalyst. The catalyst that we added was the iodide ion. So we added that. The test for oxygen, one test for oxygen, a simple test, is you put a glowing splint into the test tube where the gas is being generated, and it will cause the splint to relight. So that's the glowing splint test. The next reaction, this was the sodium bicarbonate and vinegar reaction. So the carbon dioxide put the flame out. So remember, we poured it on the flame, put the flame out. And NaHCO3 commonly, like in the kitchen, is called baking soda. So baking soda, okay. This reaction actually is a little hard to see in the form that I've written it, but it's a double replacement, and then it's followed by a decomposition. Okay, so let me just finish these up. We talked about most of these in class. It's a little hard for me to write accurately in this small space, but the next one would be potassium sulfide, binary compound, and the potassium only has one charge, so potassium sulfide. Tin has two charges, 2 or 4, so this one would be tin, 2, chloride. And the next one is ammonium iodide. So ammonium is one of the few positive polyatomic ions. Lead has 2 charges. It could be 2 or 4, so this one is 2. Lead, 2, bromide. The next one, so HBr in an aqueous solution, it's a binary acid, so the form for a binary acid is hydro, and then the brome, and you substitute ic, and then you must say the word acid, or you must write the word acid. Okay, so for this next one, phosphorus, when it's negative, is -3, and copper has 2 charges, so in this case it's the copper 2 form. So we would say copper 2, and then remember, don't say phosphate, phosphide, okay, like that. Okay, for the rest of these, so for chromium oxide, oops, that's not what I want to do. So chromium oxide is going to be Cr. In this case, the chromium is 6, and oxygen is -2, so it's going to take 3 of those. Hydrochloric acid is an aqueous solution of hydrogen chloride. Lithium sulfate like that. So lithium has just one charge and sulfate is -2. 10 for bromide, so that 4 tells us what the charge of 10 is. And because the bromide ion is -1, we know we need 4 of those. And finally for iron 3 phosphate. So phosphate's -3, and we're told here that the iron in this case is +3, so just like that. Okay, so I sort of fouled up with turning the recording part on, but anyway, at this point, I think I've multiplied correctly, so it looks like you get 8.92 times 10 to the 23rd atoms of copper. So I don't know if they sort of rigged this problem so that you'd give so that you get the same 8.92 as the density, but that looks to be right, I think. Okay, so that's all of it.